Let's torch it.
Previously on Veritasium, we learned how Hans Goldschmidt discovered that a metal oxide like rust can react with aluminum powder to produce pure liquid metal. Reactions of this type are known as thermite reactions.
Whoa! Yeah! That is crazy!
Initially, thermite found limited applications, repairing heavy machinery in remote locations. Its much more common use, the one where it's widely employed today, took a bit more convincing.
There is one sound that everyone associates with railroads. This is the sound of train wheels passing over the join between one rail and the next.
In the early days of railroads, steel mills produced rails that were around 12 meters long. Then, out in the field, these were bolted together using fish plates.
That would create these little gaps between the pieces of rail and cause this kind of like signature sound, this tatak, tatak, right? And everybody who thinks railroad thinks this tatak, 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 tatak. Even though we don't hear that anymore. But we still imagine it because it was so signature for the sound to ride on the train.
The track would flex, causing the train to rock and roll, and it would also increase the wear on the wheels and create vibrations in the tracks, so they required frequent maintenance.
So you might expect that after thermite was invented, railroads would have been excited to weld their rails together with liquid metal. But that was not the case.
They would never have the idea to weld them. If he'd come to a railroad manager and told him, I'm Dr. Hans Goldschmidt, I have a process by which I can weld your thumbs together, to these railroad managers, that would have sounded more useful than what he actually proposed, which was welding their rail.
See, the gaps between rails were considered essential because railroads are exposed to the elements all year round. So they shrink when they get cold in winter and expand in the heat of summer. An increase of 40 degrees Celsius would cause a 12-meter length of rail to grow by 6 millimeters. Without gaps in the rail, people expected kilometers of railway to expand and buckle, leading to the worst possible outcome: train derailments.
So if someone pitched, we're just going to connect all the rails together, that would be a terrible idea.
That would be a terrible idea. The longer the rail, the bigger the gap, the bigger the problem. And now somebody says, hey, I can make an infinite rail, right? That just causes an infinite problem. The first ones that were actually willing to discuss this were the tram rails. Tram rails, they're in cities, they're embedded into the streets. Tram rail is much, much smaller, so the forces are much less. So the tram rails were the first ones that were interested in how can we kind of get rid of this tatak tatak, because it's kind of annoying, in the middle of the street. That was basically the first attempts, and I think in Essen, and then later on in other cities.
For this video, I got the opportunity to weld 2 rails together using thermite, and I'm going to take you through the 8 steps in the process. First, I'll show you how I did it.
Oh, man, this is difficult.
And then we'll compare that with how the pros do it. All experiments were performed under the supervision of professionals with proper safety precautions. Okay, we are out here in the German countryside, and tonight they're going to be welding this rail. They're going to do like 150 welds tonight. When you're welding rail for real, you want to do it at the neutral temperature of the rail. That is a predefined temperature at which the rail should have no stress in it.
And it's the temperature by which that piece of track that you're welding in is supposed to have 0 tension. When it gets colder than this, there's going to be negative tension, and when it gets warmer, there's positive tension.
And since we were filming in Germany in the summer, they weld at night after the rail has cooled off. Initially, when the rails are laid out, they're placed so they are touching each other. And the first step in welding rail is therefore to create a gap into which we'll pour the liquid thermite steel. So you have to cut about 2.5 centimeters off the end of one rail. This can be done with a circular saw.
Let's do this. Cutting a rail.
Out in the field, they cut their gap with a torch.
Take a little break. Oh, that is really exhausting.
The next step is to line up the rails so the weld will make a seamless connection. Both rails have to be angled slightly up toward the gap. This is because when the liquid thermite steel is poured in, it will contract as it cools, which creates an inward pulling force. But that force won't be the same everywhere. Since there's more metal at the top, there's more force pulling the rail together there. So that's why the rails have to be angled up, so that after the liquid steel contracts, the rails will be perfectly flat.
Now you take one of the wedges and put it a little bit under the rail.
Like there? Or like this, sideways?
Sideways would be a little bit better.
Yep. Yeah,
That's fine.
Okay.
Same goes for the other side. We will check. There's no gap at the moment. We need 2.4 to 3.6 here. Hit it. But now this rail is way higher than this one, and we want to have both on the same height.
Yep.
Means now we have to hit this wedge. We do that so long until we have correct height. Okay, stop. Up.
In addition to the vertical alignment, the rails also have to be horizontally aligned.
If we take a look here, here's a large gap between the straight edge and the rails.
There's a gap there.
And they need to...
We need more of a peak this side.
Yeah.
And it's a frustrating process because trying to align them horizontally throws out the vertical alignment and vice versa. I'm lucky I had help, or I would have been here for hours. When we were finally done that, we double-checked the alignment at the head and foot of the rail, and we made a terrifying discovery.
Our rail is twisted.
Even though both rails were aligned at the top, one rail was slightly twisted relative to the other, which you can see by it not lining up at the foot.
We have a maximum tolerance that is allowed here of 2 millimeters.
Yep.
Here we have more than 2 millimeters, so we have to untwist the rail.
This, of course, threw out the vertical and horizontal alignment, so we had to do that all over again.
Are we getting closer?
A little bit more.
But out in the field, the guys align the rail so quickly and easily, it really is an art.
Now we can adjust the clamping device.
This will hold the mold shoes and preheating torch in place.
The preheating torch will sit in here,
Yeah.
and we will keep the molds in place with that arms here.
Okay.
The next step, we will align the burner.
It's really important to align the torch properly so that both sides of the rail get heated equally.
I mean, I think it looks pretty good, but maybe a little bit that way, so maybe it could go just a touch.
There's one mold and the plug for you.
Next, we'll put the molds inside the mold shoes, attach them to the clamps,
Line them up.
and align both sides. It's essential to make the seal watertight, because liquid steel is as liquid as water, but almost 8 times more dense. So if it's not sealed properly, the steel would just pour out.
It looks pretty good.
I hope so.
I didn't expect us to get it this good on our first go after just the trouble aligning the rails.
The lining the rails is one of the hardest parts at start.
It's madness. So this is sand, like beach sand.
No, it has a larger amount of clay inside. It holds in place and seals. I will start sealing this side.
Yep.
You can start sealing this side. I start sealing with hand, and I will compact it with the stamping device.
And to make sure that none of the liquid metal can spill out, we pack in additional sand all over on the sides so there's absolutely no gaps. Then it's time for one of the most crucial steps, to preheat the rail.
Put it in, tighten the screw, and then opening the valve.
We also prepared a demo behind glass so we can see into the welding process, including preheating. Preheating is essential for a few reasons. First, it gets rid of any moisture and other volatiles in the mold, which would create bubbles when the molten steel is poured in. Second, it makes both rail ends really hot, which is crucial because the rate of heat transfer depends on the difference in temperature between two materials. If we poured liquid steel in between two room temperature rails, well, the liquid steel would cool rapidly, and that's a problem.
We will heat up two pieces of rail, and we will cool down one really fast in water, and the other one we will cool down in sand, so slowly. Just to show how the hardness increases depending on the cool down time. And now you try to break it.
That's hard to bend, actually. Yeah, it's hard to bend. That's the one that was in the water.
Yeah, and we cool down it really fast. And that is how to break it. And now you see how the structure of the steel has changed. It breaks very easily.
That's because when steel cools rapidly, carbon atoms get trapped in the lattice, creating this needle-like microstructure. And that forms a kind of steel known as martensite. Martensite is really hard, but also brittle, since the lattice can no longer absorb energy without fracturing.
Now we can take a look on the clock.
Yep.
We have 1.5 minutes until we have to remove it again.
Okay.
The next step is to ignite the thermite. And it's important to do this right after we turn off the preheating.
5, 4, 3, 2, 1.
So I put the plug in the mold and then the thermite bucket on top, and then I ignited it.
Oh my goodness, no! In making these videos, the team and I often travel around the world, talking to scientists and filming at research facilities. I mean, guess where I am right now? We filmed part 1 of this video in Germany, Casper's been in the Netherlands learning about Strandbase, and Peter has just come back from trying and failing to break glass in New York. It is a great job perk, but there is one really annoying problem, which is that it's hard to stay connected with the rest of the team while we're out on location. We either have to pay ridiculous roaming charges, or find a local SIM card, or just search around for public Wi-Fi. And as you can imagine, this isn't something we really want to be dealing with while we're making a video, which is why we use this video's sponsor, Saily. Saily makes it incredibly easy and affordable to stay connected while you're abroad. You download it once, and then you can use it in over 180 countries. Just choose how much data you want, how long you want it for, and it's super quick to set up. All you have to do is select the country and the plan, then activate the eSIM, and you're done. It's also much cheaper than roaming. Then, when you land, you can automatically connect to a local network with no hidden charges, and you're able to do the important things like access maps, book a car, or make calls. So for your next trip, make sure you scan this QR code to download the app, choose a plan in the country you're traveling to, and here's the most important thing: use our code Veritasium at checkout to get an exclusive 15% off your first purchase. So scan that code, check out with code Veritasium, and get ready for traveling. So I want to say a big thank you to Saily for sponsoring this video, and now back to thermite welding. Oh my goodness! Wow!
So the thermite reaction is taking place inside. We're forming molten steel and also molten aluminum oxide.
All these demos are incredibly difficult to shoot because they're going to be many, many orders of magnitude brighter than the normal scene. So just getting exposure is a huge challenge. Something this reminds me of is that the power radiated by something thermally is proportional to temperature to the power of 4. So slight increases in temperature result in huge increases in power.
In the previous video, we showed what happened in the crucible through glass. So you can see the liquid steel and the liquid aluminum oxide forming and separating out, and then the liquid steel dropping out the bottom. Well, here we get to see that liquid steel falling into the mold. So the liquid steel comes in first, and it goes all the way to the bottom. Next, the slag starts to come out. But since aluminum oxide has a lower density than steel, it's just going to float on top and go out the sides into the slag pans. So that makes sure that we don't get any slag mixed in with the liquid steel.
That is so awesome.
Yeah.
That is just spectacular.
Whoa. Ah, that is bright.
And now we wait. We need the steel to cool long enough so that it's solid, but not too long so that the excess steel and slag is difficult to remove.
You have to get the time right. What does he think? You guys tell me it's not liquid anymore, I believe you.
Now 2 minutes passed, so let's wait 30 seconds more.
After that time has elapsed, then it's time to essentially clean up this weld. So we can remove the slag pans and the mold shoes. And we break off the top of this mold. These are really single-use molds. They get destroyed in this process.
And now you put it on side.
Put
Right
this
to the
by the slag
pans.
pans?
That's fine.
Then we used a weld shear that can create up to 20 tons of force to shear off the excess steel from the top of the weld. And after that's done, we hammered off the remaining excess parts.
That's fun, actually. I like that step.
The next step is to grind down the weld so it's exactly the same level as the rail. Obviously, you don't want any bumps when the train is going over it, but also you don't want any indents. So this grinding step is really important.
So we put on the grinding machine and grind until maximum 1 millimeter of material is left. And we try to only grind on top of the weld.
Yeah.
It's normally conducted in 2 phases. First, there's a rough grind, and then a finer grind is applied later.
And we only grinded the top surface.
Yep.
We did not grind the running flank.
Yep.
And you have to lift down the grinding device and hold everything so it's even heavier than the part we've done before. That's rough grinding right there.
I'm sweating. It's like a serious workout.
The guys in the field were obviously much better at grinding down the rail than I was. So they would move on, leaving a still glowing hot section of the rail behind them.
There probably will be millions of people watching this video. What is the likelihood that they have ridden over one of your thermite welds?
They will.
100%.
100%.
Anywhere in the world?
Anywhere in the world. Of course, there is countries
North
where
Korea.
we are not the market leader or something. But finally, they will ride above our wells.
We'll just cut it out and then take it over to the metallurgy lab.
Oh, that is heavy. Oh, that's my weld. My first thermite weld. Man, that is hot.
This is what you have done yesterday. We can now put it in the acid.
What does the acid do to the surface?
The acid attacks the steel. But because the orientation of the crystals inside the steel is not the same, the acid attacks it not in the same way everywhere. And because this is different, you can see different structures. You can see some fine structures in the rail, in the heat-affected zone, and in, let's say, the fusion zone.
Mm-hmm. Can I touch it?
Yeah.
Yeah, you can't really feel
Some
it.
micro microscopic basis.
Yeah.
You cannot feel it.
It's interesting, you can see it, but not.
Yeah.
And it's a very fine line.
I mean, you can see the different structures of the crystals even.
In the weld, you can see 3 different zones. The normal rail is on either side with a horizontal grain due to how it was rolled in the steel mill. In the middle is the thermite steel. You can still see a bit of horizontal grain, but here it doesn't come from the steel being rolled, since this just solidified from liquid. Instead, it formed from the solidification front moving from the sides to the center, and when the crystals from both sides meet, it creates tiny microscopic pores, resulting in this darker line in the center. Now, the boundary of the thermite steel isn't sharp, and that's because as the liquid steel pours in, it actually melts some of the rail. This helps it form a strong bond.
A good weld would be enough with just wet atom layer fused, but we are using the process on a construction site. And on the construction site, not everything is so good handled like in a laboratory. The gap is not 100% always the same, so we need something robust with functions on construction sites.
In Germany, regulations require melting of about 3 millimeters off each rail. The final zone is in between the normal rail and the thermite steel. This steel didn't melt, but it received enough heat that the crystal structure changed, resulting in a smaller grain structure. This is known as the heat-affected zone. If you measure the hardness across the weld, this zone is actually the weakest, both in terms of hardness and yield, the amount of force it takes to permanently deform the steel. So if a weld breaks, it's almost always here.
That's a line you could see on that macro etching. Thermite?
Yep.
That's a fusion line. And here we have now rail seal, heat affected.
Yeah.
So the structure is changed by heating up and then recrystallization of the steel.
So then I guess the question is, how strong is rail that's been welded? Well, at Goldschmidt, they actually take sections of rail that they have welded and they test them until failure.
Every 200, basically, we create one test weld, and we analyze it in terms of chemistry, we analyze it in terms of hardness, and we analyze the bending. And this is the bending press. They put this in, right? And then the force comes from top and then goes down and it breaks it. And we measure the speed and also the force.
I'd say it looks like it's flexing a bit.
So we're loading up that weld, bending it until it snaps.
See that curve go?
We want to see how much force it takes to snap and exactly where that break occurs.
140 tons? It's getting really deflected now.
Yes.
Yeah. 150 tons? Ooh, that was cool. I was just expecting a little crack, like that was catastrophic failure. Just over 150 tons.
So we think the crack propagated from the bottom upwards because it's being pushed down like that. So this is under a lot of tension.
Yes.
So it breaks under tension down here, rips up this way. And so it doesn't break in the middle of the weld. You're saying this zone beside it, which is a previous rail material that got heated up in the weld, is actually weaker.
Yes.
Every year, around 2 million welds are performed using thermite, and around half use Goldschmidt's thermite. Now, each weld creates about 2.5 centimeters of rail, so in total, that's 50 kilometers of railroad created every year out of liquid steel.
You have a very demanding process, and you have to make sure that there's certain properties with respect to bending, with respect to tension, with respect to hardness. That's a process that needs to be kind of replicated every time, a million times a year.
So with all this continuously welded rail around the world, why doesn't it buckle in summer when it heats up?
Well, that's because there's another way to change the length of the rail. Okay, imagine a piece of rail. If we use a powerful machine to push on it from both sides, it will shorten slightly. And if, on the other hand, we pull on the rail, it will lengthen. So you can use mechanical stress to change the length of the rail. The fractional change in length is called strain. And if you plot the relationship between stress and strain, you find it has a linear relationship, at least with elastic deformation. As long as the stresses applied are not too large, the rail will spring back to its original length when the stress is removed. And this is key, because as long as we do that, we have two ways to change the length, thermal and mechanical. And we can use one to compensate for the other.
When the rail thermally wants to expand, we can use mechanical forces to compress it. This is what the sleepers and the ballast are for. The sleepers pin down the rail, and the ballast locks the sleepers in place. So, as the temperature increases, the rail doesn't lengthen. Instead, the stress in the rail, the compressive stress, increases, and the rail just expands to the top and sides, which are unconstrained.
It's also interesting to note that railroads typically use as high of a neutral temperature as they can, because a rail that shrinks too much in winter and cracks under tension is less problematic than one that expands too much in summer and therefore buckles. It's also easier to detect a cracked rail using conductivity measurements than one that has buckled. So thermal expansion and contraction are counteracted by mechanical stress. That is the reason why we don't need expansion joints in railways. It allows trains to go faster with fewer bumps and vibrations and much less maintenance. Grady from Practical Engineering actually made a whole video about this, and it's excellent. I'd recommend it. So far, we've seen thermite under normal conditions.
Wow!
Conditions that are expertly tuned to protect thermite from its environment. But in the next thermite episode, we'll find out what happens when this is not the case. And we'll learn how to work with thermite under these conditions. So trust me, you don't want to miss part 3.
My hands are shaking.
Right? Make sure you're subscribed to get notified when that video comes out.